So furthering our relationships for the stress and strain, where we found that the elastic limit, the yield point, etc., etc. Now this is a very special case of the aorta, the main artery which takes and distributes blood from the heart, and I have just given it. The strain, of course, is dimensionless, so it is 0.5 and 1.0, and the stress is 0.5 and 1.0 into 10 to the power of 6 Newton per meter square. We can see that the strain goes to almost 100%. That is, so we were talking about the aorta, and we find that the strain is almost 100%. And for stresses to the tune of about 10 to the power of 6 Newton per meter square. Aorta is from the muscles around the heart, and you can see that the expansion is quite substantive over here, and you also know that the elasticity in the rubber is in fact very poor. Here also the elasticity is poor. Elasticity, if is said to be good when the modulus of elasticity is high. Anyway, so there is another case of brittle materials, and here you can see that there is the stress into strain relationship. The Hooke's law is applicable for a very short level of stress and strain, and then there is a brittle failure in the brittle case. We can also take the case of marbles. Okay, in the case of marbles, the stress into strain is proportional to stress is proportional to strain. That relationship, which should be a straight line, does not exist for most of its parts, and the marbles they give in after a certain stress, small amount of stress is applied on them. Okay. Amorphous materials, they have their own story, and normally the metals and alloys, for example, the brass and steel, they have high amounts of modulus of elasticity. Okay. Now we can work out, we can find that when the forces are applied here, then this wire or the cylinder which is subjected to these tensile or compressible forces, their area of cross section also it decreases. When they are elongated, the area of cross section is deleted, and we talk about what is known as the lateral strain. The lateral strain can be said to be longitudinal or tensile strain is delta L upon L, but lateral strain is delta D upon D, where D is the diameter. So naturally the diameter is twice the value of the radius, so we can write it as delta R upon R. Now, interestingly, the ratio of the lateral strain to longitudinal strain is a very interesting item, and that is called Poisson's ratio, sigma. Okay, so delta R upon R divided by delta L upon L, which becomes delta R into L upon R into delta L. This Poisson's ratio is normally less than half, and the typical values, they lie between 1 upon 4 and 1 upon 3, that is 0.25 to 0.33. Okay, I can see that one more item that I would like to tell you. Of course, this is what we have done before, is stress proportional to strain. So stress is F upon the force upon the area of cross section is equal to the constant of proportionality y, which is the Young's modulus, delta L upon L. So y becomes equal to Fl upon A delta L. And of course, normally, because the force applied is due to some mass hanging there, and that mass is m, so m multiplied with the acceleration due to gravity and the gravitational field near the surface of the earth, divided by the area of cross section, which is pi r square, where r is the radius of the wire or the cylinder, with cross section which is circular nature. Okay, further, I can write the bulk modulus of elasticity, and the bulk modulus of elasticity, as you know, that I can draw. There is a ball. This one is the ball, and this ball carries the volume V. Okay, and this ball, upon compression, when we apply forces, I will draw only a few of them, forces like this from all sides, normal forces, which result in a pressure, the same pressure all over the surface of the ball. Then the volume of the ball reduces, and this volume becomes equal to V minus delta V, the new volume. So the compression is to the tune of delta V meter cube. So the stress, in determining the bulk modulus, the stress is equal to the force per unit area, which is nothing but the pressure. Volume strain is equal to minus delta V upon V. Okay, minus delta V upon V, and so we can write for the bulk modulus of elasticity, capital K is equal to the stress upon strain, which can be written like that, and K becomes equal to minus PV over delta V. The reciprocal of K, that is the bulk modulus, is called compressibility. Okay, so next we talk about the shear modulus of elasticity. So let us talk about the third modulus of elasticity, which is the shear modulus of elasticity. In understanding the shearing, what we have, I have taken a cube kind of a thing. Okay, we could take a rectanguloid also, it doesn't matter, and of course in the cube all the faces have the same side lengths and also the same areas of the faces, associated with them. So I have this P, Q, R, S, the front face that we can see, and it has a back face M, N, U, V. Okay. Now this surface is fixed to some rigid body. It's not going to move unless we want it to move, and we don't want it to move. Then if we apply a force like to the pack of cards or to the book, okay, horizontally on the surface over it, then another force develops parallel to it, and we have the pair of deforming forces which are required for this kind of a deformation. Here the shape of the body will change, but the size of the body will not change. Okay. So when the forces have been applied, there is a distortion and a new thing arrives, like this and like this, these faces. And I'm saying that the displacement which has occurred over here is equal to delta L. Earlier I took it to be equal to X. So L is the length here, and delta L is the disturbance. So we can see that all these sides, they make an angle theta, 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 theta. Okay. And this theta is equal to this theta. When we make the calculation delta L upon L as the strain, it turns out to be tan theta, which is, we approximate it to theta. The area is equal to L into L. In this case, particular case, is equal to A in meter square. The force has been applied is in newtons, and the shear stress is force applied divided by the area to which the force has been applied. The shear strain turns out to be equal to delta L upon L, which is tan theta, which is approximately equal to theta because the deviation is not too much. Okay. And then we define the shear modulus of elasticity, eta. Okay. The shear modulus of elasticity, I can write it as the stress F upon A, which is in newtons per meter square. Theta, of course, it is an angle, so it is just a ratio, so it's just a number. And this is the strain. And this can be rearranged F upon A theta. And also we can write it, it's better that we always remember this kind of a formula, that stress is F upon A and the strain is delta L upon L. So that way we find out the value of eta. Okay. Many numerical question helps you attempting those, but it's just application of these formulae for y, for k, and for eta. In fact, what is happening is, when the shear force is applied, then we can consider this tube to be made up of layers and layers and layers and layers. Okay, the uppermost layer is disturbed the most, and then this is the lowermost, yani P, Q, N, M, this will be disturbed least. And then you can take a section and the disturbance will be proportional to its distance away from the fixed base, etc. These formulae which we have derived here, which come in the category of Hooke's law of elasticity, okay, These are all experimentally determined results. As I told you that the solids, they are made up of atoms and molecules. So the theory, the microscopic theory, if it is applied, then of course we can derive these formulae, and they are in consonance with the formulae that we obtain in over there. So we have 4 set of things, y, k and eta, and then the Poisson's ratio sigma. All these y, k and n, they are mLT minus 2 divided by L square. Okay, that is, they all have the unit of pressure. Sigma, of course, it is a number, and this number is less than 0.5. It normally lies, it depends from material to material, it changes, and the value is normally between 1/4 to 1/3, as I told you. And then when we assimilate all the results for y, k, eta and sigma, we find that there are some interesting relationships which we encounter. For example, k is equal to y divided by 3 into 1 minus 2 sigma. Remember, sigma cannot be more than 0.5, else this will become equal to 1, and then this factor in the denominator will become equal to 0. So sigma has to be less than 0.5. Second relation, this was the modulus of rigidity and the Young's modulus. They are related along with the Poisson's ratio, as eta is equal to y divided by 2, 1 plus sigma. You can just write 2, 1 plus sigma is equal to y upon eta, etc., etc. Okay. So these are the formulae. You may remember, but the most interesting formula is which does not contain sigma. And this connects the 3 moduli of elasticity, the Young's modulus, the bulk modulus, and the modulus of rigidity, and it turns out as 9 upon y is equal to 3 upon eta plus 1 upon k. So with that, I have not discussed any numerical things, okay, but one of the interesting examples that you can do is having a split two materials of different lengths. This is L1 length, L2, and they are subjected to the same set of forces, etc. So what is the elongation of the first one, this one, what is the elongation of L2, that if you carry out. And shortly, not very far off, I will talk about the spring constants and the combination of spring constant. No sooner than I enter into the vibrations, etc., I will deal with that in detail. So with that, we come to a close of this chapter, and next item that I am going to talk to you about is the fluids and their properties. So shortly we meet again, but I insist again that this series was started just in order that we must have some interactive sessions with bright students like you, and I am able to study, to answer you. So please, you query, we answer, you question, we answer. This is our motto. So please subscribe to that, and you may create a forum, etc., in which you can discuss with your colleagues, and that will help us enjoy. So my purpose is, my motto is that I should enjoy, you should enjoy, and you should enjoy while doing physics. Physics is not a hawa. Thank you very much.